Section 16.4.6 Solving bilinear equations. That said, I will now show you how to solve bilinear equations. The trick is to change the representation of the elements in the ring N. We have already seen several examples of how this can be done. In the ring R13, elements are represented as a plus b square root 13. Gaussian integers are represented as a plus bi. Quaternions are represented as a plus bi plus cj plus dk. Here, I, j and k are abstract units whose products determine the behavior of the ring, and a, b, c and d are commutative elements of the ring. Quaternions can be non-commutative because the multiplication of the units is not commutative. That is, ij is not equal to ji, ik is not equal to ki, and jk is not equal to kj. With only one unit, Gaussian integers are necessarily commutative. The trick is to linearize the bilinear equations by finding a representation for the non-commutative ring N. This is easily done. Start by dividing the elements of N into two sets, A and B, where A contains the elements that have representations and B contains the remaining elements. Initially, A is empty and B contains all the elements of the ring. Begin by taking the commutative elements and moving them into set A. These ring elements will represent themselves. They are the A term in the representation. Choose any remaining invertible element as the unit I. Take all of the ring elements that can be represented as A plus bi, where A and B are commutative elements of the ring, and move them from set B into set A. So far, all of the elements of A are still commutative. Set B cannot be empty because N is not commutative. We already noted that a ring with only one unit, like the Gaussian integers, must be commutative. So take a second invertible element from set B and call that the second unit, J. This time you take all elements that can be represented as A plus bi plus cj and move them from set B to set A. There may still be ring elements remaining in set B. In that case, you would repeat these steps, but for simplicity, let's suppose that 1. Only 2 units are needed, 2. All of the elements in the ring can be represented as A plus bi plus cj, where I and j are the abstract units, and 3. A, b and c are commutative elements of the ring N. In practice, the number of units you get may depend on your choice of I and j, so you should make multiple trials to get the fewest units. This is important because more units means you will have more equations when you linearize. Since the time needed to solve a set of linear equations is proportional to the cube of the number of equations, this has a large impact. Let's go back to the matrix equation Rf equals Fr and put the ring elements into the form A plus Bi plus Cj. The unknown elements of R would have the form x plus yi plus zj, where x, y and z are unknown commutative ring elements. Now a term of the matrix product Rf would have the form where I squared, j squared, ij and ji would be further expanded as linear combinations of 1, I and j, such as d plus ei plus fj. The actual expansions, of course, would depend on the choice of ring and which elements were chosen as I and j. The same must be done with the terms in the matrix product Fr. In the end, instead of 900 equations in 900 unknowns, you get 2,700 equations in 2,700 unknowns. This boosts the number of false solutions from 2 to the power 450 up to 2 to the power 1,350. This is bad news for Emily. False solutions do not allow her to recover the message. Section 16.4.7 Weaklings. The family F will include some weaklings, such as diagonal matrices and triangular matrices, which Emily can easily invert. These weaklings should not be used as keys. When choosing a matrix from the family of F, verify that there is at least one non-zero element both above and below the main diagonal. To make this test fast, just verify that at least one of x12, x13 and x23 is non-zero, and at least one of x21, x31 and x32 is non-zero. Otherwise, reject x and choose again. The percentage of matrices that get rejected is negligible. Section 16.4.8. Making it fast. The advantage of using matrices instead of exponentiation may not be clear yet. Choosing a matrix S or R from the family F requires taking a large power of the generating matrix F. How is that any better or faster than taking a large integer to a large power? The difference is preparation. In the Shamir and Massey-Omura methods, Sandra and Riva must take the number each has received from the other party and raise that to a large power. Since they do not know that number in advance, they cannot make any preparations to speed up the exponentiation. With the matrix method, however, the generating matrix F is known beforehand. Both Sandra and Riva can generate some powers of F in advance, then keep this base set of matrix powers on hand so that they can generate a new power of F just by one or two matrix multiplications. For starters, they could generate the set of 16 matrices F, F squared, F to the power 4, F to the power 8, up to F to the power 32,768 using just 15 matrix multiplications. If they did only that much, then Emily could do the same. She would have the same base set of matrices as Sandra and Riva, so she could easily determine their encryption matrices S and R. To prevent this, Sandra and Riva need to randomize their sets of matrices. They do this by choosing two of their matrices at random and multiplying them. This product will replace one of those two matrices in the base set. Sandra and Riva do this independently. Neither one knows which powers of F the other has chosen. This replacement operation should be repeated many times during setup, say 1,000 times, so that each party's set of matrices is thoroughly random. If 1,000 seems excessive, remember that in the Shamir method, using a 300-digit prime, each exponentiation will require about 1,000 multiplications and 1,000 modulo reductions. Sandra and Riva also need to keep the inverses of their matrices. Each time they multiply two of the powers of F, they need to multiply the corresponding powers of F prime, so that they never need to invert any of the powers. This setup step, generating the base set, needs to be done only once before the first message is sent. When you have this expanded set of generating matrices, you can produce a matrix for sending a message using just one multiplication for the matrix, and one for its inverse. You randomly choose two different matrices, f to the power a and f to the power b, from your base set. Multiply to get f to the power a plus b, then replace f to the power a by f to the power a plus b, so you generate different matrices each time. Using this technique, I have found that the matrix method is about 2,100 times as fast as either the Shamir or Massey-Omura exponentiation method for a 30 by 30 matrix versus a 1024-bit modulus.